We have looked at how to identify the domain of a function by making sure we omit any numbers that will produce a negative under an even root or a 0 in a denominator. For example, if we are given the following function and we input 3, the denominator would become 0, and if we put any number greater than 3, our radical would have a negative under it. So we restrict our domain to only the numbers less than 3. Our goal now is to graph functions like these that have restricted domains, but more importantly, they have some x value which makes the denominator 0. In order to make the denominator 0, our function must be a fraction. We call these types of functions rational functions since they are the ratio of two different functions. When graphing rational functions, you must include the x-intercept, the y-intercept, just like we have in previous videos. However, we must also include holes, vertical asymptotes, and horizontal asymptotes. These are newer concepts to us, so let's explore them one by one. For there to be a hole in a rational function, there must be some cancellation of a polynomial from the numerator and denominator. Here we have a rational function that has a denominator that is a difference of squares. This means that we can factor it nicely. Since we have x minus 7 in the numerator and denominator, we can cancel it out. So where is the hole in this function? To find the x-coordinate of the hole, we have to find the value which makes the cancelled term equal to 0. So if we set x minus 7 equal to 0, we find that the x-coordinate of our hole is at x equals 7. So now how do we find the y-coordinate of our hole? I do this by inputting my x-coordinate, 7, into our simplified function. If I input my x value into my non-simplified equation, it will result in a 0 in both the denominator and numerator. And this is unacceptable. So my hole is at 7, 1 over 14. I want us to look at the graph of the original equation versus the simplified equation. They're actually exactly the same, except that the original equation has a hole at 7, 1 over 14. Let's try another example. The procedure to find a hole in a function is the same. I simplify my function as much as possible and find a polynomial which cancels out. I then set said polynomial to 0 and solve for my x-coordinate. To find the y-coordinate of my hole, I input the x-coordinate into my simplified equation. Remember, don't use the original equation. Now let's inspect the graph. They're exactly the same except that the original equation has a hole in it, and that hole is located at 2, 5. A horizontal asymptote is an invisible horizontal line that creates a boundary in which the graph of our function approaches but does not touch. It is usually expressed as y equals something. And when we try to identify the horizontal asymptote of a rational function, one of three things will occur. Either the degree of the numerator is greater than the degree of the denominator, or the degree of the numerator is less than the degree of the denominator, or the degree of the numerator and denominator are the same. Each of these cases have a different impact on our graph. The first case will result in no horizontal asymptote. The second case results in a horizontal asymptote at y equals 0, aka the x-axis. And the third case creates a horizontal asymptote at y equals a over b. Now a is the leading coefficient of the numerator, and b is the leading coefficient of the denominator. Notice how for these two graphs, there are no horizontal boundaries, which our graph is trying to approach but cannot. Some students may think that this is a horizontal asymptote, but it is not, since our graph is not continuously trying to approach this line. It actually just curves away from it. Both of these graphs approach the x-axis, or y equals 0, and try their best to touch it. However, both are unable to cross that horizontal asymptote. It may look as though it touches it towards the ends of our graph, but if you zoom in, you can see that there is always space between our graph and the horizontal asymptote. For the graph on the left, we can see that we have a horizontal asymptote of 2, and for the one on the left, we can see that it has a horizontal asymptote of minus 17 over 3, which is approximately negative 5.5. Again, the graph may look like it's touching these asymptotes towards the ends, but I can assure you that they are not. When we say our graph cannot cross the horizontal asymptote, we usually mean for large numbers of x, or as x approaches infinity. This means locally, there may be values for which our graph can cross the horizontal asymptote. Let's look at the graph of this function. Since the degree of the numerator and denominator are the same, we can identify the horizontal asymptote as the ratio of the leading coefficients. To find if our function crosses our horizontal asymptote, set our function equal to 3 and then solve for x. Vertical asymptotes are invisible vertical lines which our graph tries to touch but cannot. It is usually expressed as x equals something. Unlike horizontal asymptotes where there can only be one, there can be multiple vertical asymptotes, and it's important to identify them all. The reason why we have a vertical asymptote is because our graph cannot take on a certain value, which will make the denominator 0. For instance, given the graph 1 over x, what value of x will make the denominator 0? Well, 0. This means that 0 is a number that we want to remove from our function's domain, and our graph is doing everything it can to avoid having 0 as an input. Look on the left-hand side. As we get closer and closer to 0, what do our y values do? Our y values get smaller and smaller all the way down to negative infinity. And on the right-hand side, my inputs get larger and larger towards positive infinity. They're doing everything they can to avoid having x as an input. Let's look at the function 1 over x plus 7. What value will make the denominator 0 here? Minus 7. So minus 7 is a number that we want to remove from our domain, and our graph will do everything in its power to avoid having minus 7 as an input. Notice on the left-hand side of minus 7, my output becomes infinitely small, while on the right-hand side, my outputs become infinitely large. How about the function 7x divided by x squared plus 3x minus 4? Well, we can factor this bottom polynomial, and then we can see that there are two numbers that can make the denominator 0. So our graph will have two vertical asymptotes. Again, these are numbers that we must remove from our function's domain, and our graph does everything to avoid having those numbers as an input. Now let's put all those skills together. When we choose points to plot, always choose x values that are close to our asymptotes.